Hi, very good afternoon to all of you, and thank you for joining us today. A very special thanks to Professor Sachchida Nand Tripathi. Thank you, sir, for coming to IIT Gandhinagar and delivering this lecture. This is a part of the KPCSD Distinguished Speaker Seminar and Infosys Lecture Series. Um, Professor S.N. Tripathi has won the Infosys Prize 2023 laureate in Engineering and Computer Science. Uh, Today, we have students, faculty, and many of the people from other organizations joining us. We also have a group of participants from the DST Summer School joining us today. I would briefly mention about the Infosys Prize Lecture Series. The Infosys Prize Lecture Series is intended as a platform for the Infosys Prize laureates to speak about their award winning research to a wider audience of research scholars and students. The lectures are meant to spark conversations and enable an exchange of ideas among the scholarly community and aspiring researchers. The Infosys Science Foundation, which gives the Infosys Prize, was set up in 2009. The Infosys Prize is an annual award to honor outstanding achievements of researchers and scientists in 6 categories: engineering and computer science, humanities and social sciences, life sciences, mathematical sciences, and physical sciences. From 2024, the ISF is moving in a new direction and awarding early career researchers aged 40 years and below. The foundation works with communities of students, educators, and others to create conversations around science and research. The foundation is attempting to foster dialogue around science and society through talks, workshops, initiatives, performances, and other events. Our events are a part of this larger objective to spark conversations and kindle curiosity about science and scientists. And regarding the KPCST Distinguished Speaker Seminar, it brings prominent scholars and professionals in the areas of sustainability to the IIT Gandhinagar campus to discuss their works, perspectives, and thoughts on sustainable development. The series is designed for a broad public audience, and the topics and treatment are targeted for a general audience. So I would now like to invite Professor C.N. Pandey, who is the coordinator of the Center for Sustainable Development, to please deliver a welcome note to the participants. Thank you, sir.
Thank you very much, Fagani. Good afternoon, all of you. After the lunch, I think we have already spent 1 hour or so. This is the right time to have this lecture series. Today's distinguished speaker, Professor Sachchida Nand Tripathi ji, who is professor in IIT Kanpur and a very eminent fellow who is here. All the faculty members from IIT Gandhinagar who are present here, all the faculty members from other universities and institutions which are around who have joined here, all the researchers, scholars, and students. It really gives a great pleasure to me to invite Professor Tripathi on behalf of the Center for Sustainable Development. Center for Sustainable Development is a center created in the IIT Gandhinagar about 5.5 years ago. And as the name suggests, this is a center which has to do whatever it can do, practically speaking. There is no limit on what it can do. So, related to sustainability, climate change, and all. I'm very happy that apart from the distinguished speaker series that we are having, there's another lecture series which is Infosys Prize lecture series. And with the efforts of Professor Bimal Mishra, he really worked hard for this. And with the efforts of Professor Tripathi also, the two things are converging today in this lecture. And this is going to be a very important thing in meeting the objectives of the Sustainable Center, because the Sustainable Center has a number of thrust area. It's not only an important distinguished lecture, but one of the thrust areas is air pollution, the pollution in general, and sorry, air pollution in particular, and we are going to listen to Professor Pathak about this. The Professor Pathak is Professor Tripathi is a professor in IIT Kanpur, and he is in he's doing a great work there. A very eminent person, very well-known person. He has visited IIT Gandhinagar in the past also, and with this, I welcome all of you again, and I welcome Professor Tripathi also to this, and I'm very sure that we will all learn a lot and enjoy this lecture. Thank you very, very much. Thank you so much.
Thank you, sir. I would now like to invite Professor Vimal Mishra, who is the Vikram Sarabhai Chair Professor in Civil Engineering Department at IIT Gandhinagar, to please introduce today's speaker, Professor Tripathi, and we can then start the talk. Thank you.
All right, so I've been asked to speak a little bit loudly. So I'm doing that. Good evening, everybody. So I can say that after a long time we have an event, all tickets are sold out. So the room is completely full, house full. And this is real great thing. So thank you for coming today evening. And it's my privilege and honor to introduce Professor Tripathi formally for this Infosys Prize lecture today. And let me do this honor. So Infosys Prize 2023 laureate in engineering and computer science, Professor Sachchida Nand Tripathi is professor, joint faculty in civil engineering and sustainable energy engineering at Indian Institute of Technology, Kanpur. Professor Tripathi was awarded the Infosys Prize for his work in the deployment of large-scale sensor-based air quality network and mobile laboratory for hyper-local measurement of pollution, data generation, and analysis using artificial intelligence and machine learning for effective air quality management and citizen awareness, and for the delivery of new pathways of aerosol formation and growth that provide mechanistic understanding of haze formation. In his Infosys Prize lecture today, he will demonstrate the utility of sensor-based dense network in air quality management. In this lecture, Professor Tripathi will present results from 1400 nodes operational network in Uttar Pradesh and Bihar. He will also discuss the use of AI and ML-based end-to-end data-driven solutions, including sensor calibration, fault detection, optimized network size and location. Professor Tripathi will discuss ongoing research and findings. So apart from Infosys Prize 2023, Professor Tripathi has a long list of several achievements, including the Fellow of Institute of Advancement Sustainability Studies, Germany, J.C. Bose National Fellowship, several faculty chair positions during his tenure at IIT Kanpur. He is elected fellow of Indian National Science Academy. He received UP Ratna Award from Government of Uttar Pradesh. He was awarded Distinguished Alumnus Award from Banaras Hindu University. He is also elected fellow of National Academy of Sciences, India. So apart from that, he is also fellow of National Academy of Engineering. He received the Shanti Sarup Bhatnagar Prize in Earth, Atmospheric, Ocean, and Planetary Science in 2014. And very recently, in fact, yesterday or day before yesterday, he received M. Visvesvaraya Chairship from Ministry of Water Resources, which is now Jal Shakti Ministry, Government of India. So I can read more about him, but you all can probably search him in Google, look at his Wikipedia page, get to know more about his work and himself. But I'll stop here in interest of time, and it's my privilege and honor once again to welcome Professor Tripathi. And now over to you, sir. Please.
I wanted to do something for the environment. and that inspired me to study air quality and air pollution. I focused mainly on studying aerosols, as it was central to understanding air quality. Air pollution is a major hazard in India and around the world, and it is important we solve it right now. We need to make policies effective, bring science into them, and devise new metrics that can be monitored at scale. Mitigation measures should move from lab to pilot and finally should be scaled up. I believe that what we are doing should be shared with the common people for their understanding. So thank you IIT Gandhinagar for hosting me here as part of Infosys laureate talk. And of course, I'm very grateful that most of the faculty members, a lot of faculty members, students who are here, who could make it, my friends from PRL and other places, they have been my long collaborator. So I'm very glad to see you guys here. So this work, what I'm going to present is actually an effort of students, many collaborators inside IIT Kanpur and of course outside IIT Kanpur. In fact, also some international collaboration which we have established over a period of time. And that is what I'm going to show you in next 40 to 50 minutes, what we have done in last possibly 5 to 6 years of the work. So what we are going to do, that I'm going to discuss a class of problems which comes when you want to use sensors because we know that these sensors are very kind of cost effective. Maybe in terms of cost, they are about 1/50th of the regulatory grade monitors, government monitors which currently is being used for monitoring air quality. And therefore, there are quite a few problems which we need to address to overcome the problem of accuracy, precision, etc. So some of the problems what I'm going to discuss here in this talk is that how do we bring the accuracy of the data which you monitor and measure using sensors on par with the regulatory grade monitor, given the fact that you have a cost difference which runs from 25 to 50 times. So that's one class of regression problem. And then also one can divide into two, that where one is that if you have the problem of that co-locate, that a sensor is located next to a government monitor, so you can have supervised learning problem. And second, where you do not have this affordability, that because you do not have so many government monitors. So there is an unsupervised problem. Unsupervised learning, we want to correct the data by learning amongst themselves, right? So that's a different class of problem. Second, as you see, is a problem of optimization, that once you have or one when you have government monitors, few, for example, let's say Ahmedabad, and you have money to just put 2-3 government monitors, and then you use common sense, you put one monitor maybe in a development community, one near a commercial place, another next to a road, and you are, because you got 3 contrasting settings and then you monitor it. But if you have like intent to monitor it as scale and you want to put 50 or 100 sensors, then how do you put it? Where do you want to put it so that in limited resource, you can maximize the outcome, that is information, citizen satisfaction. So then it becomes the problem of optimization. So that is what also we are going to discuss it, that if you have a fixed sensor, that you just put the sensor and it stays there all along its lifetime and you monitor. So that's one class of problem, one class of optimization problem. The second problem is that where, for example, you want to monitor pollution on the curb side or road side. And you know that as the vehicle move, depending on the volume of the flow, pollution may change. And thereby, you want to monitor it in some kind of a mobile sensors or a mobile laboratory. So that's the second class of optimization problem. We have addressed that also, and probably it's very unique globally. I will discuss that as well. Second broad class is classification. That is where you have the data, and now there's the emerging, you can say, technology or an approach
where you want
get some idea about groups. And when I say group, means it's called Airshed. Just like some of you may be aware, Professor Mishra is here, he works a lot on water problems, and we know there's something called watershed. That if you know
watershed, water flow, etc., behaves in a similar way. Just like that, there is a new concept which is emerging and is very, very critical in having very efficient air quality management in place is called Airshed, which is basically an area
where air quality or pollution behaves in a similar way, which is an outcome of interplays between weather, sources, and orography, etc. But how do you recognize that? If you have only few data points, of course you cannot work it out. But if you have large number of data, there is a possibility that you apply, again, machine learning methods. I will show some examples, nice examples, that can group these air sheds in a very nice way. And then it gives you a very good handle that how do you plan the monitoring, and thereby then how do you kind of formulate air quality management in and around that airshed. And one airshed could be different from others. So in a way, it can also help you conserve resources as well, right? That's another thing. We also have worked on source detection. That is, one thing is to know the hotspots, the level of pollution, but it is far more crucial to understand where are the sources, which are the sources, and where are they located. So once you know that, that gives you another lever to go after sources, plug them, mitigate them. Okay, so that is also, we have made some progress. And then finally, when you have lots of data, then you become more greedy about the data. Right? Like everything in life, once you have it, you want more. It's a very simple thing. So likewise, when you have data, but there are data gaps. As I said, that these are sensors and they may be broken, there can be fault, or they may go out of the calibration curve. So how do you basically work with that? You basically work again with what is well known within the data science community is called imputation. We call it generally, who are not actually, who haven't been working in data science earlier, is called interpolation problem, right? So that is what also we have worked. And then I also will show you some results from forecasting. That if you have so much of data, can you be able to forecast it? Okay, so these are some of the problems, and with some results that we have already published or we are in the process of publishing it, I will show you that. So here is what you see is a interesting project we are working on. It's called Amrit, air monitoring of rural areas using indigenous technology. And this is what you see is a combined map of Uttar Pradesh and Bihar, right? And these red that symbols show the government monitors, where government is monitoring, and these are called basically regulatory grade monitors. And if you put the numbers here together, 57, 35, there were 90 odd government monitors which are currently located in these two states, where about 38, 350, what you call, lakhs people actually reside, million people reside, 38 crores, okay, 380 million people reside. This is almost like 1/3 of India's population or something like that. So what we have done here, we have actually developed these sensors, which is, as I said, is a much smaller, very compact, in collaboration with few startups. I've been working, our groups have been working for quite some time. And then we have actually put it in every block of these two states. So in essence, we have actually put 826 sensors in Uttar Pradesh in as many blocks, which are across 75 districts of Uttar Pradesh. In fact, a day before or something, we have completed that deployment. And in Bihar is about 539 sensors, and which got completed last September. So since last September, about now 9 or 10 months ago, we are getting good amount of data across Bihar from these sensors. And for about 2 seasons, we are getting reasonably dense data streaming. These data is getting streamed in real time to IT campus server, and then of course variety of things we are doing with our group members
members and other collaborators at IIT Kanpur and also sometimes outside. Okay. So first class of problem, I said that if you have large number of these entities as a very well-known problem, how are you going to basically locate it? I said that if you have few objects, you can use heuristics. But if you have large number, then there comes that you try to formulate the problem. And this is a very well formulated, you can say, well-established optimization problem. But we have made use of it in getting an optimized, efficient network that can give you good amount of air quality data, which meets your need while conserving resources. So that is the way we formulate this problem. Basically, we created, as you know, an objective function, which intends to maximize citizens' satisfaction. So what citizen wants? Anybody, when you go outside, once you know air quality is bad for you, you want that I must monitor what I am breathing in, right? But everyone cannot monitor unless you all have a personalized sensor with you, which is not possible. So of course, that could become possible in future, but as of now, this is not possible. So what are we going to do? And we are going to place these sensors in a way so that everyone feels happy, but in a very objective way. That's why I said that we want to formulate. So there is a whole set of mathematics that has entered into that. And then you have certain constraints. And the constraints being that do you want to put it near hospital, or you want to put near schools, or in the community area, or near roads. These are all basically kind of choices you have to make, right? Depending on how many sensors you have. The second thing is that what is your budget? If you have infinite budget, you can put infinite number of sensors, but you don't have that luxury. So these two are constraints, and I already mentioned about that what function you want to maximize. And we solve this problem using two approaches. One, of course, has been used in this field for some time. Not a lot of people have used it. It's called a greedy algorithm. And second, on the right, is called a genetic algorithm. And using that, we solved this for Surat city, which was a very interesting problem. In fact, it was approached, they approached with this problem in mind that a part of Surat city where they had certain amount of information, which is called emission inventory, which is how much or what is the rate of emissions of particulate matter or gases in every grid, and they want to monitor it. And they said, if I have this much money, please advise us where do we place it so that we actually meet our goals. And that is what we did it. And these two you see in a way show that where you want to basically place your sensors. Now, as I said that is one class of problem where you want to have fixed sensors to monitor air quality. The second problem comes, as I said, that when the pollution over a period of time is variable, right? And the period of time has to be short. We know that pollution also varies over city. But over a period of a day, there is some variation. But day after day, we know generally we see a similar trend unless there is some kind of changes, be it in weather or sources or something else. But when you want to look at the exposure, what we see as you move on the road, things vary as you move, right? Depending on what is the level of the traffic, whether it's congestion or there's no congestion, whether you are standing on a traffic light. So many things which vary over a period of 15 minutes to an hour. So very short level and acute exposure also is very well known can cause severe issues with human health. And this is what we try to look at this problem here is first to kind of model. So this is a very established way to model traffic flow. The first thing you want to model is what is the traffic flow. This is the model which people have done over a period of time. They have chosen a model city which is called Sivasspor. It's a US city. It's a well-designed city with a well-designed road and arteries network. And where we modeled it and we found that, well, our model is looking quite well. The second task was then to get what is the emissions coming out from this traffic flow. So we got that right. That is what is shown in this right hand top and bottom figure at 2 times. T is equal to 3, T is equal to 5. These are normalized time, so you don't have to worry about its unit. And what you see that there are number of these light blue nodes where you could locate your sensors to monitor what's happening about pollution. And the dark blue actually shows where your genetic algorithm is telling that you monitor, right? So what you see that the pollution is changing over a period of time. At T is equal to 3, you see that pollution is very high on the top left corner, and then it's quite high on the right bottom corner. But as probably based on the traffic flow, the way traffic is moved across all these roads, so these are all lines joining are basically kind of the arteries, etc. through which traffic is moving in. And what you see that over a period of time, now instead of 30, the 31 has a small hot spot that is emerging there. And this algorithm is quite nicely kind of advising us that from T is equal to 3, where we have put sensors at 2, 8, 9, and 21 here, and 30, and then the 37, 49, and 55. Now the algorithm is telling us that how do we move the sensors, and that one example is clearly here, that at T is equal to 5, move the sensor to 31st node, right? So that is kind of interesting application which we have shown. How do I go back? Sorry, okay. Now it's working again. That's interesting. So here again is an example of basically how the dynamic sensors can be placed to monitor pollution. But this is again shown for city of Lucknow. So city of Lucknow, we had a good number of sensors, and we got the data. Based on that, we have actually made that plot here. What you see, these are basically showing hotspot, etc. So that again, the idea being here is that as you move over a period of time, if the pollution hotspot is changing, how we can basically move the sensors to have better monitoring, so that we can have a better understanding what's going on, who is going to expose, etc. Right. So that was one kind of class of problem which I just discussed briefly. Second class is, as I said, that how do we establish some kind of a relationship between sensors measure data and the regulatory grade measure data, monitor based data, right? That is what we wanted to do when we started looking into this problem. And this is a very simple kind of technique we have used, simplest what we all do, that if you have two independent data sets, and you want to basically kind of fit a regression in it. You want to regress it and the fit a curve. And what we have done here, we have fitted the simplest possible kind of polynomial, which is linear. So what you see here, this data is for Kanpur, and you see it's for monsoon for different averaging periods, 1 hour, 24 hour, pre-monsoon and post-monsoon, because we all know that depending on the rain and many other things, pollution changes. On the x-axis, you have this accurate data that is from government kind of monitor, and on the y-axis, you have the particulate matter 2.5, which is an important indicator of pollution. And I was just kind of assuming that you know it. So this is what we are doing here, is that we are monitoring PM 2.5 here, and we are trying to look what kind of relationship we have and whether it changes from season to season, and whether it has other dependence, that is some other factors, some other independent variables or features, whether they are also kind of influencing this relationship, right? So we found very interesting that there is a linear relationship, and it depends to a certain extent on temperature, but it has a high dependence on relative humidity, and there is a whole physics behind it, that lots of water vapor can make particles grow, and thereby it can actually kind of distort, change the relationship or the calibration curve between these two things what we are doing. So interestingly, this was possibly the first paper on this particular topic and US EPA, Environmental Protection Agency, which is our their US equivalent to India's regulatory body, which is here, Central Pollution Control Board. They have adopted this to apply a cross sensors network, which already they are co-opting to monitor particulate matter 2.5 in addition to whatever thousands plus regulatory grade monitors they have deployed across US. I would say that is an interesting outcome of this. This is now a similar thing, but we are plotting it slightly differently, but don't get too much scared with that. Here what we are doing that we are changing from PM 2.5 to different kind of gaseous pollutants, as you all see here. It's called ozone and nitrogen oxide. These two are also important pollutants. So government actually monitors 4-5 kind of pollutants. In this case, here is ozone and nitrogen oxides. And what we have done here, that by placing these sensors next to the regulatory grade monitors, which we call gas analyzers, and then by applying different kind of machine learning techniques. So what you see that these different violin curves are starting from a linear model. This is the very first curve. And then all the way we have gone up to the k nearest neighbor kind of model, which is more data hungry, but a lot more accurate model. And what you see that one thing is very clear, that we can establish a good relationship between that accurate monitor for monitoring ozone, which is a very important pollutant, and also sensors, which we are using again in this case. And we are seeing that important or more data hungry models are certainly able to bring the error down. So what you see that these are basically error distribution. Both blue and orange curves are showing error distribution across the y-axis. And what you see that if you look into the mean and median of it, you see that as you move from NW, KR, and KN and D, progressively the error is coming down. Okay? So that is what was another, I would say, a very interesting outcome of that. Of course, for gas sensor calibration, we have to still go a long way from there, but definitely this was one step progress in that direction, where we can eventually move to a hybrid monitoring where the regulatory grade expensive monitors can be augmented by these sensor-based systems. Now, I mentioned earlier that you do not have always the luxury to co-locate or place a sensor next to a government monitor. That's not an easy thing because you don't have so many government monitors, right? So this becomes a problem of what is called well-known. It's a known class of problem which is called unsupervised learning. And this is what we showed here. We had an opportunity to place about 40 sensors across Mumbai city. And they had about just 14 government monitors. And we took very limited data from the co-locations. We developed a model, and then we refined this model, which is a very new approach. We just got this paper published in a very nice IIT journal, where we use this interesting model, which is called histogram loss, combined with what is called as min-max entropy. Okay, so these are basically two classes of machine learning models which were weaved together to kind of train this using very limited data. So we are talking about only 2 or 3 days of co-location. That gives you hardly 36 or 24 data points you get over hourly scale in a day. And you multiply by 2 days, maybe 48, at the most 72 data points. But they were good enough using this kind of approach to correct the sensor data where a co-location was not happening. What you see here that I am showing in all these 3 curves, there are plots where there are 3 curves here. What one you see is the blue one, which is the reference grade, the most accurate data. Second is that uncalibrated low-cost sensor data, which is the orange curve. And what you can immediately see that in all 3 plots, there is a huge difference between uncalibrated, okay, and that accurate data. But when we applied this histogram loss model on that, which is the green curve, what you see that green curve has started picking up the trend with the blue, and most of the time, in fact, it is able to bridge that gap, what has been seen earlier in the orange and the blue curve. So this is a kind of probably again a first attempt to basically demonstrate the power of unsupervised learning to train and then correct data from these frugal, very kind of inexpensive sensor data. And then, of course, hopefully, there will be many more such efforts so that then sensors become a way of doing increased or enhanced monitoring across cities. And this is already happening, by the way, at several places. This is in that direction. There is another effort again is going on in Uttar Pradesh where we have kind of deployed this carbon monoxide. So all these what I'm mentioning, these are all part of important criteria for intent. When you look at AQI, I should have mentioned it before. When you look at anywhere that's coming blinking on these displays, you see that AQI, air quality index. It is basically a weighted average of particulate matter, which is most important, and mostly four gases, which are I showed already: ozone, nitrogen oxides, carbon monoxide, and sulfur dioxide. So mainly four gases and particulate matter. So if you are able to monitor them well, I'm sure you are able to get their location well, hopefully, and then you can design device mitigation plan. That is what all we are after, to save humans' life, animals' life, and many more. So this is effort going on about how we can actually use again sensors to monitor carbon monoxide calibration as well. And without going into too much detail, our key idea that whatever I talked earlier, that we were able to get an accurate data from sensor, either when we have large number of sensors network, problem of unsupervised learning, or if the sensor is placed next to a government monitor, which we call as supervised learning, right? Now here, what we are doing is that if you have some supervised learning available, or you can make use of it, that there is a accurate monitor and there is a sensor, you are able to put them together, maybe for one location or two locations. Whether using this kind of data, we can create a more generalized model, which is not specific to, let's say, IIT campus in Gandhinagar or IIM campus in Ahmedabad, but this model is able to revise, improvise sensor data wherever you are monitoring across Ahmedabad and Gandhinagar. That's the idea. That is what we call a global calibration model. And do we have some success in that? And that's what I'm going to show you. Okay. So what you see that on the top right, again, using a kind of a, let's say, a set of or summation of linear regression model, you see for a particular location where we had supervised learning available, we are getting excellent R-squared score, 0.9. So locally, certainly problem is very well solved. But when we have data, let's say, available across these in the table, what you see across four sides, and when we try to develop this model and apply to other sides, whether that there is some generalizability of the model which you can achieve or not, that is the major question, right? So if you look across the rows in this table, what you find that if I have trained my data, or basically model, at CSIR, it gives us good result, of course, over CSIR, but it gives good result across other sites. Let's not worry about the name of these sites. It's true for 3 rows, but when I go to 4th row, it shows that, well, model actually is kind of getting a little bit unstable. Now, this is another class of problem which we are kind of working now, and I'll just show you that one result what we have, that instead of using only one kind of that linear models, if we use different linear models and we very suitably choose the weight. So this is another class. So lots of things what I'm using here is basically done with lots of data scientists at IIT, right? They are super strong. So what is done here is that you choose right weights and apply it to these linear models and then try to put them together. And we have got some success over here. That you see there are these blues are predictions and reds are ground truth done across site. And already results show that we are getting improved results. What is the next step here? The next step is that you have done this exercise, you have achieved this exercise across maybe one season, but you are not sure that it will work also for winter if you have done it for summer. So the model, the actual global model should not be biased about a season or about the location, etc. That's the idea which we are working on, and hopefully I think we should have a kind of a reasonable success on this. Okay. So I said that a lot of effort first, and I will be talking about is that how do you correct the data? Because if you do not have correct data, as all of you which are sitting here, scientists, engineer, or even social scientists, that if you do not have correct data, accurate data, or if you do not know how erroneous your data is, you would not know whether your results or inferences are correct or not. You would not be able to kind of classify it, qualify it. That is how lots of effort we are putting here to make data, what we are measuring, is more and more accurate. This is the first example I'm showing across the network over Bihar, which I just talked about. That you have about 450 sensors which are giving the data. Out of 250 sensors, we have used measurements, and just using that measurement, because remember that if you look at these blue dots, across these 250 sensors in Bihar, we had only 4 these government monitors which were giving us reasonably accurate data. So it's not that only sensor give you sometimes inaccurate data. Government monitors data also could be wrong. So you have to be very careful when you use any data, be it regulatory data monitor or anything. So we have applied a lot of tests, and we found that maybe out of n number, and it is small here, n number of monitors, and we have only 4 or 5 which are giving reasonably good data. So then we used what you see here, a broad class of these unsupervised learning techniques. What you see, these are mentioned here: Gaussian progress regression, which is a kind of a front runner for this class of problem. But just to check that whether other kind of techniques can also work, which is support vector regression, and many others we try. And these we are showing you here that how this looks R squared, that again how well these corrected sensors data are picking the trend, what is seen in these government monitors. And what you see that across these 3 locations, across these blue dot, we are seeing that Gaussian progress regression is showing some promise. This is what we have already submitted to a conference, and hopefully, I think we'll continue this work, right? Another interesting thing now, slightly moving away from calibration, is how do we recognize or predict whether a sensor is giving wrong data or whether there is a problem in sensor. So there can be 2 things which might be happening with sensors. The one problem I already spoke a lot, that sensor might have drifted. So you have applied a calibration, you tried to accurate it, comes another kind of setting, environmental setting, another type of weather, and the 2 curves, calibration start drifting. That's one problem. The second problem could be there can be a hardware failure. Now you can imagine that when you are putting this crore plus kind of government monitors, you can always maintain and do all that, but it's so expensive you cannot really expand it. But when you are putting few hundreds of these sensors, certainly it's important to anticipate, or more, even better, you can, if you are able to predict it, that it is going to fail this time, you can take precautionary measures in advance to probably do something about it, do some online troubleshooting so that basically sensors do not undergo that kind of erroneous phase. And this is what we have tried. This is the first attempt I will again say that which is happening in this kind of arena, is that we have looked into, again, a broad class of machine learning algorithms we have applied. And what you see on the right top, that there is this pitch shape where you see there are large gaps happening. And our goal was to predict it in advance. And we found that yes, this problem can also be attempted, if not fully solved. We are still working on that. So what I'm trying to just do here is that I to give you that if you have whether air quality or any data, when you have these data coming in, which are large in volume with very high speed, so you can see that every day they are giving you about gigabytes of data. So because these sensors give you every minute of data, we are able to store every 2 or 3 minutes, and we average them, and we basically finally use for analysis hourly data. And when they are coming from thousands of locations, you can understand that this is like a good treat to anybody who is working in data science, right? Now, all these machine learning techniques, algorithms which you are using could be used for any such problem when you are using data, where you need to correct the data, where you need to interpolate the data, you need to forecast the data, regardless of whether it's air quality or anything, you could certainly apply. Of course, that what you are using as an input, what you are using as features, they may vary. So here, weather, topography, many other things are important. Maybe for some other problem, some other things. But this is as a complex problem as one could think of, given the uncertain, very rapidly changing atmospheric dynamics and many other things which influence air quality, as we all know. Right? So I mentioned about earlier that if you have lots of data, can you group them? Can you classify them into different Airsheds? I already gave some background about that. And why we are after that? Because I said that if you know that Gujarat has these 3-4 airsheds, or let's say Gujarat and Rajasthan and Maharashtra, they know that they have some airshed which are distinct from each other. But there is a common airshed. So common airshed could be between Rajasthan and Gujarat, and there can be a common airshed between Gujarat and Maharashtra. Then you can imagine that the two state agencies can come together. They can, of course, pool in their resources, and ensuing information can be used in a way to have better management than they doing their things alone. So this is not only collaborative for the sake of collaboration approach, but it is actually based on a hard science, which is I'm just showing you here, that we have been seeing over Bihar that over various seasons using more than one techniques well established, like we are using LSTM followed by hierarchical clustering, that similar airshed is emerging. And you don't want to believe that, so I just show you. So if you look here, that 3 seasons we are showing you: October, November, December, February, and March, May. So 2 months, 3 months, and 3 months over Bihar, and you see that each data is color is showing. Basically, one, the value of particulate matter 2.5, and second, all the data, hourly data we have got, thousands of data points over this period from that block, right? And it has been fed into long, short-term memory, LSTM, and followed by hierarchical clustering, which I showed in the earlier slide. I will not go into that in much detail. And what you see, that there are clear clusters which are emerging over here. Now, we cannot call them airshed. Of course, nomenclature can be an issue of some discussion. You can call it micro airshed. But what you see, that over northwest Bihar and over southeast Bihar, there are about 6-7 districts in north and about 8-10 districts which have a common airshed. Wouldn't you think that in that case, only one district trying to do something to alleviate the air pollution problem, then they should come together and work together? This is what exactly, and this is not the first time we are doing. That concept is already being used extensively by California, and that their regulatory board, they don't call their regulatory board, they call it California Air Resource Board, which is a body they have created to basically make their air quality better over California. But no one has used this data-driven approach to give you idea about it. Right? This is the first time we are saying they have just tried to look at emissions, look at weather, try to impose, and then they say, okay, here are some districts we call, and then they call this, okay, this is an air district. But the air district is different from actual district. So just imagine that you have Gandhinagar and you have Ahmedabad. But then there is another kind of formation which is based on the formation or flow of air pollution, which is distinct from Ahmedabad. Now that makes sense because air pollution will not follow that basically administrative boundaries of Ahmedabad and Gandhinagar. So Californians, they realized that they started kind of working on that, but in a very presumptive way that, oh, we just divide it that way because we have some information. But since we have good amount of data, we thought, well, let's do it in a little better. Okay. So another problem is, I said that human is of paramount importance, and we know that air quality over long run, poor air quality kills people. Okay, so if you don't know the data, I think it's very much in public domain, and Lancet and WHO over and time again they have said that across the world air pollution has become the single most killer, right? So 8.5 million premature deaths, what WHO and Lancet they ascribe to that data, that is what is happening across the globe, and this number is somewhere around 1.8 million to 1.9 million in India. So very important issue is that can we predict humans exposure of PM 2.5? So remember I talked about these 5 pollutants, but amongst them PM 2.5 is the most lethal. 90% of the human health related issues can be subscribed to only PM 2.5, right? So this is what one attempt we are doing over Bihar. I'm just giving you some example that how one can using this dense set of data and then other data set. So this is not a first attempt. Some people have done it before. They call it land regression modeling. But what is first time here is a ground based measurement at a very granular level. That is, every block we are getting. So the model has this kind of test or a benchmark against which it can be tested. Right? That is what we are trying to do here. So what you see, if you look using all this model without going into that detail, what you see that on the left you have HH, that is at midnight, then you have 8 AM morning, and then you have 16, which is 4 PM afternoon. What could be the pollution for a particular day? I don't remember what day it is, over Bihar. That is what we are showing here. And this prediction using all these kind of features, many things what you see on the left top, that block is shown, is done at a scale of 100 square meter or half a square kilometer. So this is probably best you could do. Now if you imagine that if you superimpose the population density of Bihar here, you have clear idea that which half square kilometer is exposed to the most acute air pollution, right? And then you can accordingly, if you have will, if you have ways and with wherewithals, then of course you will start acting on that. This is the another thing which we are working on. But what I'll show you here, another interesting thing, that another way to look at this thing is what people do is that they kind of combine that exposure data, which is PM 2.5 at a high resolution level, with population density by giving a weight to it. And this is called population weighted exposure, right? And you see, this is so interesting that we have shaded southern part of Bihar in yellow. So the white is North Bihar. And what you see that population weighted concentration in microgram per meter cube is plotted for those 3 duration of the day in the upper panel for the North Bihar and the bottom panel for southern Bihar. You see, there is a striking difference in terms of population weighted concentration or exposure over these 2 regions of Bihar. This is so interesting to me, right? So these several such things we can do to understand about environmental issues using data, exposure to people, and then we can of course take corrective measures by having proper policy measures in place, and then other things then follow, right? Another thing I said that I will discuss briefly, that there is a kind of a belief in India that air quality is an urban problem. And it's right to think so, because we think that most of the polluting sources sit or are located in cities, be it traffic, industries on periphery, or some other things, right? So this is also an important question to ask, that whether there is a difference between urban and rural air quality, or they are sometimes similar, right? That is what we wanted to look by using all the data we have over Uttar Pradesh and Bihar, and I'll be showing that here. But first, what you need to do is to determine which areas are rural and which are not rural, or in other case, which are urban. And that is what we have done here in this plot, that we used some of very established technique, which are all shown here, to kind of designate or label every block, whether it is a rural or urban. And then that subsequent table which is shown on this left bottom is basically an outcome after applying these classification techniques based on satellite and many more other data. And interestingly, then we try to validate it with a classification which Government of India uses. For all these blocks, they also have their own ways to establish whether it's rural, urban or semi-urban, which is actually used by Ministry of Urban and Housing Affairs and some other ministries. And actually there was a very strong correlation which was seen between this data and what GOI uses. And based on that, what you see that this whole map is basically kind of categorized, binned into urban, suburban, small town and rural across these two states. And what we found that this is some result which we are still looking into carefully. But if you notice that Uttar Pradesh, for all these four categories, you do see some differences. Of course, it's not visible here, but there is some. Urban is higher, and actually it is statistically also significant. But over Bihar, what you see, the green curve is above the red and yellow. This is something everyone, I think, should be surprised if you are not. That what are these things? Apart from, we know that pollution will flow, and when it flows from cities, of course, it will cross over Airshed, where there are villages and there are rural areas as well. So they can also be impacted. But in addition to that, whether there are sources which are operating inside rural landscape, which are responsible for giving rise to such findings, that is something we want to see. And interestingly, I'm not showing here that what you see, there is a very strong, interesting diurnal pattern across all four regions, which we have seen that has a strong, striking agreement with the two peaks, what you are seeing here across four seasons over 500 plus stations, is closely resembling with the household related emission data developed by an independent group. That exactly timing and the nature of the curve is showing. That shows that lots of rural and small town related peaks are being contributed from household related activities and ensuing emissions. So that is what is another interesting thing what we are working on. And another thing I should point out, that when we try to look at a district scale, this diurnality, that there is a striking peak which is coming around mid-noon, and that is seen very clearly in emission. And you can imagine that, and that's only rural area, because we all know that in rural areas many times people also cook during daytime, right? So that is something quite interesting we are getting here, okay? So I will skip that. This is about a forecasting problem, so there is a lot of kind of model related details. I will not discuss in detail here, but I'll just tell you that there is some progress, that you have so much data. So definitely there will be interest that we try to forecast it, that given you have a time series, we all know you are always have interest that if you have a data measured at t, you always like to predict t plus f. So this is a well-established problem everywhere, be it electricity consumption or weather, and we are trying to do that here. On the right, these 4 actually panels are basically showing that only, that how well we are able to predict in 72 hours in advance. And certainly, I will not say that, well, we have got full success, but it does show progress and, kind of something interesting using different kind of models, right? So, I will now shift to a little bit going away from the only sensor based results. I'll show now something about a haze here, because I think I have only 7 minutes left. In the beginning, I said that Delhi's haze is distinctly different from the haze which they have seen over China, because that is the closest to discuss here. So, what we have done that, of course, Professor Neeraj Rastogi is here from PRL. He was our collaborator and co-author on this paper. What we had done that over a long period of time in Delhi, we monitored particle size distribution over Delhi. Okay, so we all can understand these are very tiny things from 1 nanometer, half nanometer to few micron, very, very small particles, but they have a distribution. Just like you talk about any data sample, there is a distribution. They also have a distribution, which is number or mass varies with size. And there is a large variation, right? And so what we wanted to understand how this distribution changes, what causes it, because that would contribute to haze formation. Because over a period of time, anybody who has been watching Delhi's haze problem must have seen that starting October, middle of October, you have reasonably okay kind of air quality until 5-6 p.m. every day. But then from 20th October, 25th October, depending on many other factors, suddenly after 6 p.m., 8 p.m., 9 p.m., that air quality deteriorates. And those are the 3-4 weeks we all know that particulate matter 2.5 concentration suddenly shoots from 60, 70, 80 microgram per meter cube to 200, 250, 300, 350 microgram per meter cube. That is what we say is a haze, where not only we feel very kind of a suffocating atmosphere, environment, but visibility goes down and many other things happen. Our main question here was that what is causing that haze, right? And is it different from other places? That is what we looked here. What you see that in the first plot is basically growth rate of these tiny particles, which you see in nanometer per hour. So using these kind of measurements of size distributions, there are instruments now, some are actually being used also at IIT Gandhinagar. You can precisely compute these growth rates. That is what you see we have done over different size bins, 25, 40, up to 100, which we call nanoparticle, and then greater than 100. Of course, you can also compute that. And for a comparison, we have also plotted the same thing across globe for similar areas, that is yellow urban, that orange is urban, yellow is also urban, but that's urban polluted, that's P, and rural and remote. And what you notice that over Delhi, we have seen very high level of growth. That is up to 35 nanometer per hour. So when there was a haze event, we saw that particulate matter 2.5, particularly nanoparticle, which you clearly see in 40 to 60 nanometer, is growing at almost same rate what their size are. So every hour they add similar amount of, kind of diameter, and it just adds more and more to mass, right? Now, another plot here is again shown just to give you a kind of a sense that what is happening elsewhere. You see those dark red, that dark red just above, just at the right, top corner is 1 and 2. And that shows that you have all nanoparticle growth, and then there are prolonged nanoparticle growth, which are happening like over whole night. You see these data points are again falling at a very, in a extreme space where we have plotted growth rate versus condensation stream, right? So it showed that we had a much higher growth rate that's happening over Delhi compared to anywhere else in the world. People have seen over China up to 10 nanometer per hour, but that's during daytime. I should point out that these are all happening over Delhi in night time. Daytime growth is plausible, has been explained using arguments of photochemistry, that whatever organic gases are in the atmosphere will kind of form another kind of organic gases which are having molecular weight, low vapor pressure, can go and condense on particle. But this is something is a very unusual and therefore very surprising, intriguing, I would say, because it's happening in night time. And what we could do is that using another set of instruments, so there's a lot of detail here, chemistry, but I don't want to go into all the details here, that we actually also can clearly do the chemical profiling of these nanoparticles below 100 nanometer and above 100 nanometer, that is for nanoparticles and particles which are little larger. And then simultaneously, by looking at the gas data, which is shown here, that which are actually contributing to the particle formation, we could clearly identify this biomass, primary biomass burning, which gives rise to one particular gas. Most of the chemists who are here will know is called levoglucosan, and we can monitor, measure it in both gas phase and also which has already condensed into particle phase. We could find out that it's the primary condensation of primary gases which are coming from biomass is particularly causing this rapid rise between, as I said, 4 to 8 hours, which eventually forms this haze, and then it just, sometimes sustains over days, and you know that what happens to that time in Delhi and NCR atmosphere. Okay, so I'll skip that as well. I should also quickly actually tell that what other kind of technologies you can now do to understand sources in a way that gives you dynamic information, right? And I said that if you know the source, you can design plans, you can have strong mitigative actions that you can take to improve air quality. So one kind of technology you can say that what we are working on is called basically dynamic hyper source apportionment. I don't have much time to explain that, but where the idea is that by placing these little advanced kind of monitors, mass spectrometers inside a mobile laboratory, which is able to give you chemical fingerprints of particles, and that is well known that it can help you get source contribution very, very accurately, but it is very expensive proposition. So what we are trying to do that once you have put these instruments on a mobile laboratory, it allows you to take it around anywhere. For example, I can place it today in IIT Gandhinagar, and 7 days or 8 days of data is actually required to get this source, profiling. I can take then 5-10 kilometers away from Gandhinagar to another site where probably sources are distinct. And I can keep doing that. And every location where I'm taking my mobile laboratory, I can place sensors. And I talked a lot about sensors, right? And I can use this chemical fingerprint data to train sensor. And then I take away mobile laboratory, but my machine learning model, which is trained, can help sensors to start predicting source contribution. This is what we call a new technique as dynamic hyper source apportionment. Okay, that is dynamic because sensor give you information every minute, every hour. So therefore, once they are trained enough, it can give you source information, every hour. And it's hyper because you can actually spread out sensors almost everywhere, 100 places, 200 places. So once you have, if you are able to train the model at 4, 5, 6 distinct locations, then most of the places actually similar kind of models should be applicable. I talked something of that kind in the context of carbon monoxide sensor calibration. And this is what currently we are working on, and we have a reasonable success over Lucknow. I'm just showing you here that just look how using the RTSA, near an industrial place, first let me just give you one idea that these two pies is a very interesting that near industrial place we are getting a very new source which is an industrial organic aerosol. I have never seen here, I don't know whether anybody has seen that before, that in a city you just get another factor which is totally distinct and it is bringing signature of the industrial area. And if you want to get at a very high frequency, that is what you see here, that it can differentiate from ferrous smelting to e-waste incineration to informal metal recycling, so many things. And the key thing is that whether you can recognize these peaks in the time series and when it's happening and where it is happening. And that is what is an important thing, because unless these kind of information is handy with the regulatory board, with the municipal corporation, we will always be struggling, we'll always be chasing the problem. We need to get ahead of this problem, right? This is similar thing which I have worked, of course, Professor Lokesh Sahu is here. We collaborated a lot using his PTRMS, so much so that we broke his PTRMS. So now he has fixed it. So we have got this gas source, VOC source information, and of course, has got also some interesting result. I think I will just, final slide here, I'll show that, because we discussed a lot about health related impacts. So this is one work we have done with my former PhD student who is the first author of this Nature Communications paper, Deepika Bhattu. And then this work she continued, or actually she started in a collaborative project with her host at PSI when she was a postdoc over there, and now she is a faculty member at IIT Jodhpur. Here what we have done is that many things I already have talked about, that if we can get very granular source information of particulate matter, and which was done over a very extensive geographical area. So what you see that right from Haryana on one end, which is northwest, to the southeast Kanpur, we had 4 to 5 sites where we had simultaneous measurements from January 2018 to May 2018. So huge amount of data, and we could get source information. But key thing was that we actually worked on, I'll just go to that looking at a particular metric which is called oxidative potential. And Neeraj is here, he works a lot on that, Professor Neeraj Sugri from PRL, that oxidative potential is emerging as a very important metric, better than PM 2.5. Okay, so remember that lots of these people's human health response, and that is basically looked by exposure response, that given this much of exposure, what's the response of people by monitoring people's health over a long period of time. And that is how you try to predict human's health. But now a whole body of research now has emerged that says that better than PM 2.5, it is its chemical composition, or even better if you are able to measure oxidative potential, which is a important proxy for actually measuring reactive oxygenated species, which tells you that the species which are present in particulate matter, how harmful they are for your lung cells. So if you have more reactive oxygenated species, that means they will react more and they will kill your cells more, right? Simply speaking. And this is what, using this chemical data across 5 sites from Haryana to Kanpur, about 1100 kilometers over 5 months, we could clearly tell that what is it which is driving these presence of reactive oxygenated species in PM 2.5, okay? And how different it is from in terms of determining humans' response to these, what you call harmful species. And the conclusion was that lot of these are because of the local incomplete combustions, right? It's not regional, it's not because of transport. Lot of things what you burn close by has a disproportionate contribution to the oxygenated species. So it's like that you might have a lot of PM 2.5, And lot means, of course, not a lot, but and you plot it as an exposure on x-axis and response on y, that 2 PM2.5, a more and a less might have a more acute response depending on what it is composed of. That is what is telling. That is what information coming from these measurements of reactive oxygenated species. That is, if it has material which is generated from incomplete combustion, that can give rise to high reactive oxygenated species, and thereby it can damage our cells more. Okay, that is what is the key finding. So I will just stop it here, and I'll be happy to take some questions. Sorry, I think I took out.
Yeah, Dr. Tripathi ji, fabulous talk. And guess just about that rural areas, you talk that during daytime also in the rural areas PM 2.5 is very high, and due to this is like that local household activities you told. I have noted it at least in UP and Bihar. Nowadays, there is a very dense road network is being developed, and for development of the road network, there is so many hot mix plants are put, and they all are put into the rural areas. So they are also contributing. We have seen near Lucknow, Sitapur, Lakhimpur, our places. There are at least 20 in that stretch, that all in the rural areas. So that also could be contributing to the increased daytime PM 2.5 into rural areas. That was just my look angle towards that.
Yeah, I think that's very much possible. See, what we have seen is a ground-based, reasonably accurate measurements, right? And what we have found corroborative is from a different group emission data, but only due to household activity related emissions, correct?
Yeah.
And that is able to match to certain extent, but that correlation could be fortuitous.
Yeah.
That is explaining, but that alone cannot explain this, right? So we need one, as you rightly said, we need other emissions data, but that's very difficult. We cannot have all these bituminous and all these mixed plant related emissions. So the other only possibility is that we feed these emissions into a transport model, that is like a kind of good chemistry model, and try to see that what other factors are contributing to these peaks, the timing of the peaks, etc. And that is what we should try to do. And that
just
is what
very
we'll be
small
doing.
one thing, that whether these sensors, wherever they put, some weather parameters are also being measured with these sensors, these PM 2 point sensors which you have put very nicely in the UP and Bihar, whether any that these sensors are having some inbuilt weather parameters also, at least basic parameter, temperature, pressure, TPQW, whether these are
Each box sensor has PM 2.5, PM 10, temperature and relative humidity.
okay.
Yes.
Thank you.
Yeah, I'm here. I'm GH Tripathi from Gujarat Pollution Control Board. So, sir, you equipped your sensor particularly with a government monitoring stations. So, I think government stations data is a secondary data for your this thing development.
Sorry, second sentence I didn't get you. Government data? What
government monitoring data.
Yeah.
So that you have taken from the government department,
Yes.
particularly from UP and
Right
Bihar.
from-
So that is a
from
secondary
the-
data for you.
Yeah, from the regulatory boards. From the
the
boards,
pollution
yeah.
control board.
Yeah.
So whether that data is accurate or not, your sensor data, if it is depending, calibration is on government data, then I think there is a big issue.
Yeah, you are right. That's why I said that any data what comes to your, to do something about, one should first look at the veracity of the data and accuracy. So first thing we do that. But I should have told, I didn't have so much time, that before taking sensors from the laboratory, IIT Kanpur, to place in the field, we first do a calibration at IIT Kanpur. We have a test bed. We have 3 test beds where we have our own monitors like what you use, that BAMs. We place them, we develop a calibration factor there over a period of 2 weeks to 4 weeks. then only we take to the field. And I said that that's why, if you remember, I showed a map where there were about 200 red dots and only few blue dots were there over Bihar, because we may have had more government monitors, but when you look into the data, quality and assurance, we found that many of those monitors did not have reliably enough data to be used. So, and you can look at it. There are ways, as you know, right? So, we are very careful about when even we are using the government monitor data from any location. Manual one we don't use, because manual data monitor, as you know very well, gives you one data point a week or two. Now that's very small, right? So our sensor is giving data every minute, but generally we use for most of the analysis purposes hourly data. So we have to basically rely on the CAA QMS data.
Yeah, that's fine. So that is a NCAP program is there. So for every million cities there should be a fire station or something like that.
Right. Anybody else? Yeah. Professor Sanjeev.
Thank you, Professor Tripathi. It was an excellent talk. I was just wondering about these villages of Bihar behaving differently than villages of UP. So, like you said that in UP, the rural pollution is less in rural areas than the urban areas, whereas in the Bihar, rural Bihar is more polluted than the urban Bihar. I mean, how do you explain this kind of a dogma? And another thing is like...
Sorry, what is your question?
So you said in your data, the urban Uttar Pradesh is less polluted than the, more polluted than the rural Uttar Pradesh. Whereas in the Bihar, the rural Bihar is more polluted than the urban Bihar. Let us say a village near Patna is more polluted than Patna itself. At least
and your question is why?
Yeah. And even if you try to explain it through the transport model, as you said, do you think the transport of pattern is different in UP than in the Bihar? Because they all are in the Indo-Gangetic plain. I don't see how that can be different.
No, so they are all in Indo-Gangetic plain. So there are some common features, we know that. But then there are some distinct features, right? So we have to look for that. For example, we know that rural Bihar, the cooking practices, the penetration of LPG, etc., is different. We had another project which is not related to that, where we had done a large household survey driven, kind of study, where we in UP and Bihar, and we have good idea that what's the LPG penetration in these two states. We also know that the level of industrialization in Uttar Pradesh and Bihar is very different. So they all, in a way, will contribute to what we are seeing in the data. And these are basically data not from 1-2 data point. They are from 400 to 400 plus in Bihar and 600 plus stations from UP. Now, transport, when I said it's not only transport, it's basically transport and chemistry. So it's a full, like a software.
I just have one observation. Maybe you can check from your people who have installed. When you say that we're installed at the block level, now you are installing in a block, which is a small township, then that I agree can be as polluted as Patna, for example. But if you go really far away from a block, a small town, then LPG penetration is quite a bit high right now in Bihar, frankly. So, I mean, I'm just it was a very kind of an anomalous observation. So, I thought it's better to discuss.
All right. Thank you. Any other questions? Yeah, Professor Arvind, and then
Thank
Professor
you.
Pandey.
So thank you, Professor Tripathi, for a wonderful talk. So I have something similar for what that Sanjeev has said, but I have also one observation from a table that you have given about this UP and Bihar urban rural classification and two more subgroups. And to me, it looks like that the ratio of rural population to urban population is higher in Bihar compared to that in UP. And could that be the reason, simplistically?
Could be. I mean, we didn't look that. The classification scheme, as you know, was that night light adjusted with something, NDVI. And second was a built-up area ratio. So these are the two basically people use. I mean, they use one of them. We have tried to bring both together. And then that outcome was that what we found this classification, and this matched I said, reasonably well what government of India is doing. And that is where we had to take a call, I mean, otherwise you just keep on classifying it, right? So that is what we have done. But definitely we'll also see that if that
Maybe it is a
factor
factor of just population.
Yes, we'll look at that. Yeah.
Yeah, Professor Pandey. Yeah.
Thank you very much, Professor Tripathi. It was an excellent talk, full of information and wisdom and new things. Your team and yourself are really working very hard. My compliments for that. So it was a wonderful talk and with a lot of good information. One information which everybody talking about is the urban-rural, the divide that you have presented. I have some 1 or 2 points about that. They may not be correct, but there's just 1 or 2 thoughts about this. The particulate matter 2.5 pollution is largely dependent on the location of industries. The location of industrial activity is not necessarily close to urban areas, not necessarily close to rural areas. So the pattern is different in different areas. For example, if you move in Gujarat, the number of industrial estates are in fact close to the cities. Okay, they are not very far from the cities. They are called GIDC areas and all. But this is not the situation in Bihar or in UP, where the industries tend to get located near the rural areas, because the land is cheaper there and there are so many reasons. So the permission is easy to get there. So they are close there. Some industries are typically in rural areas. For example, the brick industry. Okay, they're typically in villages, and they're very crude and they emit a lot of PM 2.5, and that is the cause. Then the development activities going on in rural areas a lot. In fact, there was a report on the consumption of cement in rural areas immediately after or during the COVID period, because a lot of migrant laborers were working in Bombay, Delhi and all. They had to leave those places, and they were the great story. They all went to the villages in Bihar and UP. Many of them have never returned to Bombay, Delhi and all. So they have not returned. So they have gone to their houses. Their houses were kacha houses. They thought that now we'll permanently live there. They had some money, and therefore there was a huge pattern of conversion of kacha houses in these villages, poor villages, into pakka houses, leading to a lot of construction activity. There is a rural road network which is going on. I mean, we hear from Nitin Gadkari's performance that making highways and all, but equally impressive is the rural road link network. So some construction there is going on in some way or the other in the villages also. The water pipelines which are being led, through different programs of the government, they're doing a lot of digging. If you go to any village now, then you will find that the road has been broken because the pipeline is going, the drainage line is going, and so many things are happening. So, frankly, I'm not very surprised, that the PM 2.5 emission in Bihar is much more than this. Then the last point is that the rural landscape is very diverse, so probably some more factors. For example, the presence of forest area in the rural landscape, the presence of water body, large rivers. This UP and Bihar both have huge river basins, so the presence of large rivers and the water bodies and all these things also probably could contribute to the diversity of rural area. So probably rural area should be studied in more stratified manner, rather than as one cluster. So these are some of the points I wanted.
Thank you.
And so anybody from students, any questions? This is going to be the last question.
Sir, you have extensively discussed on PM 2.5. Does this sensor and algorithm perform well on the PM 10 also?
So we had looked over PM 10 accuracy using BAM as well as some other research grade instruments, not only regulatory grade but research grade, and we published that. And there we found that certainly PM10 still has a long way to go before it can come close to regulatory grade related measurements, okay, or based measurements. But that was some time ago, 2017-18. As you know, that sensors are developing very fast, right? The whole ecosystem. Now, there are some new sensors which I think they claim that they are able to more accurately measure PM10, and we are yet to look into that. We haven't started looking.
We have also undertaken one research project on low-cost sensor in Surat. So we found that they are quite accurate on the PM 2.5 part, but still the factor between PM10 and 2.5 was not that much equivalent to the manual monitoring or CAQMS. That's why I just asked you. And another question
You
is,
are looking mostly in at plant tower or plant tower and Sensorian. Alpha sense, which generally we use for gas monitoring, right? If you use the latest version of Alpha Sense PM10, that is claiming to have better accuracy than others. You may try some. We are also hopefully will be trying that soon.
and sir, one other question: how
All
government
right,
is
thank
using
you.
this
So,
data?
so please,
Just last
you
question.
you may discuss more. We will break for tea after this session, and you will get enough opportunity to ask more questions. I know everybody is having a lot of questions, given that the interest of topic. Yeah. So now. Yeah, so thank you once again. Let's thank Professor Tripathi once again. And now I would invite Professor Arun Singh to facilitate Professor Tripathi and present a token of our appreciation, a small memento. Thank you.